Okay, so today I want to start section 10.3, which is of matrices and systems of linear equations. So what is exactly a matrix? When we say a matrix, basically a matrix is an array of numbers. Those numbers are listed like in the row and column order. So A11, that's the entry in the first row, first column, first row, second column, first row, third column, first row, nth column, and so on. Second row, first column, second, and second, n. And then depending on how many rows you have, so AM1, AM2, up to AMN. So this is called an M by N matrix. M by N is the order of the matrix, M is the number of rows, and N is the number of columns. Always in that order. Okay? Always in that order. So just to give you an example about matrices, if I give you this 4, 5, 3, 5, 2, 3, 6, 2, 4, 1. This is a 2-row 2 by 5 matrix. That's the order. And these are actually letter grades for a statistics class versus gender. So you can see 4 male students got A, 3 female students got A, 6 female students got B. So we can use matrices to summarize data, among other things. Okay, what exactly is a square matrix? When we say square matrix, that means the rows equals number of columns. So it's 2 by 2, 3 by 3, and so on. An example, 3, 1, 5, 2, 1, 2, 3, 5, 7. This is a 3 by 3 square matrix, 3 rows, 3 columns. And the entries along the first row, first column, second row, second column, third row, third column are called the diagonal of a matrix. We only talk about diagonal if it's a square matrix, okay? And we include in the diagonal those entries that are in the first row, first column, second row, second column, third row, third column, and so on. No. A matrix with one row and several columns is called a row matrix. This is called a row matrix. Why? Because it has one row and several columns. A column matrix is a matrix with one column and several rows. This is called column matrix. Okay, what is an augmented matrix? And that's what we should focus on because most of our work is based on augmented matrix. And augmented matrix is a matrix derived from a system of equations, from a system of linear equations, whether it's 2 by 2, 3 by 3, and so on, each written in general form. As follows. So for example, how do we write the augmented matrix for this system of equations? X minus 3y equals 1, x plus 2y equals 5. The equivalent augmented matrix for this system. Okay, first you want to make sure it's in standard form, x, y, constant. So you put the coefficients of x in the first column, the coefficients of y in the second column, and then the constants and the third, and you put a line. That line tells me that there's equal sign there. Okay, so this is x, y, constant. So once we look at an augmented matrix, each row of an augmented matrix is an equation of the system. 1x minus 3y equals 1. 1x plus 2y equals 5. Okay, and the matrix with the coefficients of x and coefficients of y is called coefficient matrix. So if the matrix does not include the constants, it's called coefficient matrix. Okay, now elementary row operations. These are the operations that we will use in order to reduce a matrix to a certain form that we're going to talk about. Elementary row operations. So we should know these operations by heart. Okay, remember, if we have an augmented matrix, each row is equation. Okay, so any one of the following row operations applied to an augmented matrix, the key is having augmented matrix, not just any matrix, produces an equivalent augmented matrix, produces an equivalent augmented matrix. The first elementary row operation is interchanging any two rows. If we interchange any two rows of an augmented matrix, we get, if we interchange R1, row 1 and row 2, if we interchange them, we get 1, 2, 5, 1, negative 3, 1. It's like interchanging two equations. It's not going to change anything, okay? If you multiply any row by any non-zero constant, multiply any row by any non-zero constant, because we can times any equation of a systemic equation by any number we want. Same thing, a row. We can times any row of an augmented matrix by any constant we want. That's not going to change the matrix. And then adding a multiple of one row to another row. Adding a multiple of one row to another row will not change the augmented matrix. Because remember, say we want to, say I have a system of equations. 2x minus 3y equals 1, x plus y equals 5. If I want to eliminate y, I would times this equation by 3 and then add it to the top equation. So we're adding a multiple of the second equation to the first equation. So we can add a multiple of one row to another row and nothing will change. That's what we're talking about. Okay? So keep those three operations in mind. They're very important. So here's an example to clarify this. So given the augmented matrix, how do I know it's augmented? We have the line in there. 4, negative 8, 12. Perform the row operations and write the new matrix. So the row operation that I want you to do is take the second row and times it by a quarter and give it to the second row. So if I do that, then I will get, so I'm not changing the first row. I'm timesing the second row by a quarter times 4, a quarter times negative 8, and a quarter times 12. And is this one of the elementary row operations? It is. It's multiplying any row by a non-zero constant. Okay, so as long as it's one of these, we're good. Okay? Interchange row 1 with row 2. Now we're always working with the newest one. We don't go back there. So interchange row 1 with row 2. So we're gonna get 1, -2, 3, and then 7, 4, 3. And then number 3, so I have this 7, 4, 3. Now I want to do -7 R1 plus R2 to go over R2. So I'm adding a multiple of R1 to R2, okay? Adding a multiple of one row to another row is okay. So we're going to do that. So we're going to do -7 times R1 and then add it to R2. So -7 times 1 is -7 plus 7 is 0. -7 times -2 is 14 plus 4 is 18. -7 times 3 is -21 plus 3 is -18. Okay, so we gotta get familiar with those operations. We're gonna practice a lot of them. Here's another example. Given this matrix 2, 1, -1, it's just 3 systems of equations, and then 4, 3, 2, 3. This is what we want to do. We're going to do these two operations. We're going to times the first row by -3 and add it to the second row, and that will be my new second row. And then we're going to times the first row by -2, add it to the third row, and that's going to go to the third row. So let's do the math over here. So usually the command is next to the row that we're going to change. So we're going to change rows 2 and 3. We're keeping row 1. So we're going to do -3 times R1 and add it to R2. So -6, right? -6 plus 3 is -3, and -3 plus 1 is -2, and then 3 plus 1 is 4, and then 9 plus 0 is 9. Then we'll do -2 times 2 is -4 plus 4 is 0, -2 plus 3 is 1. 2 plus 2 is 4, and then 6 plus 3 is 6 plus 3 is 9. Okay. Should be 9. Okay. So now we're going to use those elementary row operations to solving systems of equations. Okay, so there are two methods for solving systems of equations. There they are right here on the handout in your note. I'm going to write them down. Okay, so let's go over those two methods. The first one is called Gauss elimination method, which uses row echelon form of a matrix, then back substitution. What does row echelon form mean? A matrix is in row echelon form, REF, if the first non-zero number in each row is 1. The leading entry has to be 1. So 0, 1, 2, 3, 0, 0, 1, 0, 0, 0, 0, 0. So this is in row echelon form. Why is that? Because the first non-zero number in each row is 1. This is the first non-zero number. This is the first non-zero number. There's no non-zero here. The leading entry in each row is to the right of the leading entry in the row immediately above it. You can see this is to the right of that. Okay. All rows consisting entirely of zeros are located at the bottom of the matrix. That's called row echelon form. Now, reduced row echelon form, which is used by Gauss-Jordan. Gauss did row echelon form by himself, then him and Jordan did that simultaneously. They did reduced row echelon form. Instead of REF, they did RREF, reduced row echelon form. A matrix is in reduced row echelon form. If it is in row echelon form, which means it follows all this, every entry above and below each leading entry is a 0. So this is not in reduced row echelon form because this too must be a 0 to be in reduced row echelon form. Okay, every entry above below each leading entry has to be a 0. So something like this. This is a reduced row echelon form. Okay, this is reduced row echelon form. Okay, so let's add number 3, page 709. 14, page 709. It says a matrix is given, determine whether the matrix is in row echelon form, determine whether the matrix is in reduced row echelon form, and write the system of equations for which the given matrix is the augmented matrix. So 1, 3, row 1, negative 3, 5. The first non-entry 0 is a 1, the first non-entry 0 is a 1. And there are rows of 0, so it is row echelon form. And system of equations equals negative 3, 0x plus y equals 5. It's not reduced row echelon form because this leading entry doesn't have a 0 above it. Okay. Number 18. 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3. This is reduced row echelon form. So the first non-leading entry is a 1, and they go to the right as you move downward, and there's zeros above and below that, those ones. So it is in reduced row echelon form. X equals 1, y equals 2. You see why it's important? Then you have the solution right there. Okay, so now how do we solve a system of equations using Gauss elimination method? To solve a system of equations, to solve a system of equations using Gauss elimination method. So you have a system of two equations, a11x plus a12y equals c1, a21x plus a22y equals c2. The first thing you want to do is write it as an augmented matrix. So you're going to have a11, a21, a12, a22 equal c1, c2. And then to get it in row echelon form, because you're using Gauss elimination method, you're going to start by making a11 equal 0, make a11 equal 1. The first non-zero entry should be a 1. How do you make this a 1? The elementary row operations. If there's a 1 at the bottom, you interchange the rows. If there's not a 1, you might have to multiply, and you can, like if this is a 3, you can multiply by 1/3, or you can add a multiple of one row to another row. Okay, so you get this one, and then you get the one underneath it to be 0, then a21 equals 0, so you go like this, and then like that, so counterclockwise, okay, and then a22 equals 1, and then if you have to go to make this 0, you can do it, so in that order, 1, 0, 1, 0, okay, 1, 0, 1, 0, and use the elementary row operations to do that. But you want to get your 1 first within each column. You got your 1 and then your zeros, your 1 and then your 0, okay? Always do column by column and get the 1 first and then the zeros. Okay. So use Gauss elimination or Gauss Jordan, it doesn't matter. To solve, 3x equals 1 plus 2y, y equals 2 minus x. The first thing we want to do is write them in general form. 3x minus 2y equals 1, x plus y equals 2. Okay, then we want to do the augmented matrix. 3, 1, negative 2, 1, 1, 2. So we want to get this to be a 1. Luckily, we have a 1 here, so we can interchange row 1 with row 2. We get the 1 up there. 1, 1, 2, 3, negative 2, 1. So remember, we go column by column. We get our 1, then our 0. To get a 0, it's always a good idea to add a multiple of the row with the 1 to that row. So a multiple of 1 is negative 3 to make this a 0. So negative 3 R1 plus R2. We want to take over R2. So we're not changing the first row. We want to change this into 0. Negative 3 plus 3 is 0. Negative 3 plus negative 2, negative 5. Negative 6 plus 1 is negative 5. So we got our first column. Now we go here and I get this to be a 1. If we switch rows 1 and 2, we're back to square 1. You don't want to do that, not anymore. This is done. So we want to times this by negative 1/5 to make it a 1. So 1, 1, 2, 1/5 times 0, that's 1, and that's 1. Now we can stop here. We don't have to make that a 0, although we could. So at this point, we can write the system of equation. Look how easy it is to solve now. X plus y equals 2, y equals 1. So if y equals 1, that means x is also 1. And we've solved the system. Now for 3 by 3, same idea. I'm not going to write it down here. So you're going to write the augmented matrix, then you get your 1, and then zeros, then you get your 8 to 2 to be 1, and then zeros, then you get this to be 1, and then zeros. That's a lot of work, okay? In that order. Okay? So here's an example. Now on the test, you can use Gauss or Gauss-Jordan. You can do it row echelon form or reduced row echelon form. It doesn't matter. Gauss-Jordan. Elimination. So to solve, x minus 3z is negative 2. 2x plus 2y plus z is 4. 3x plus y minus 2z is 5. Now we want to write it, so we're missing a y, so we're going to put a 0y in there. And we're putting our coefficients 1, 2, 3, 0, 2, 1, negative 3, 1, negative 2 equal negative 2, 4, 5. We already have a 1 up here. I want to make these two zeros. So we're going to times this one by negative 2 and add it to the second row. And we're going to times this one by negative 3 and add it to the third row to get the third row. So the first row is not changing. Negative 2 plus 2 is 0. 0 plus 2 is 2. 6 plus 1 is 7. 4 plus 4 is 8. And then negative 3 plus 3 is 0. 0 plus 1 is 1. 9 plus negative 2 is 7. And then 6 plus 5 is 11. Okay, so we got the first column, 1 and then zeros. Now we want this one to be up here. We can swap rows 2 and 3 because the zeros are not going to change anything. Row 2 with row 3. So we get 1, 0, negative 3, negative 2, 0, 1, 7, 11, 0, 2, 7, 8. We got 1, we got 0, now we need to make this a 0, so we times this one. To make a 0, we always times the 1 in that column by the opposite of that number. So we need a negative 2 times the second row added to the third row to be in the third row. Let me put the math over here. So 1, 0, negative 3, negative 2, 0, 1, 7, 11. 0 plus 0 is 0, negative 2 plus 2 is 0, negative 14 plus 7 is negative 7, and then negative 2 plus 8 is negative 14. Okay, so we got this, we got that. Now over here, to get the 1, we can times the whole row by negative 1 over 7. Okay, so 1, 0, negative 3, negative 2, 0, 1, 7, 11, 0, 0, 1, and 2. Now to get these to be zeros, if I want to go all the way, we can stop here if I wanted to, but if I want to go all the way, I wanted this to be 0 and I wanted this to be 0, so I'll use this one times this one by negative 7. So negative 7 R3 plus R2, so R2. And then to make this a 0, we're going to times this by 3, 3R3, 3 times R3 plus R1 to R1. So that's right, R3, we're not changing that. We're doing 0 plus 0 is 0 plus 1. Negative 7 plus 7 is 0. Negative 14 plus 11 is negative 3. Then we're doing 3 times 0 is 0 plus 1, 0. That's 0. 3 plus 1 times 1 plus negative 3 is 6 plus negative 2 is 4. So you can see that's a 1. You can see that x is 4, y is negative 3, and z is 2. Okay. Now let's look at a system that has no solution. System with no solution. How do we know that? Let's look. So how do we solve 2x minus 4y plus z equals 3? X minus 3y plus z equals 5. And 3x minus 7y plus 2z equals 12. So we're going to write the augmented matrix. You know what I'm going to do to save me the headache? I'm going to do the second equation as the first row. That way I would have my 1 without having to swap it. And then 2, negative 4, 1, 3, and then 3, negative 7, 2, 12. Just save a step, okay? So I wrote second equation first, then this, then that. Who cares? So I skip a step. We got the 1, and we're going to get these to be zeros. So negative 2 R1 plus R2, and then negative 3 R1 plus R2. So 1, negative 3, 1, 5. Negative 2 plus 2 is 0. 6 plus negative 4 is 2. Negative 2 plus 1 is negative 1. Negative 10 plus 3 is negative 7. Negative 3 plus 3 is 0. 9 plus negative 7 is 2. Negative 3 plus 2 is negative 1. Negative 15, that's negative 3. Okay, so we got this column. Now over here, we're gonna we are going to, we want this to be a 1. So we're going to times it by 1/2 the second row. So it would be 1, negative 3, 1, 5, 0, 1, negative 1/2, negative 7 over 2, 0, 2, negative 1, negative 3. So we got this one. Now we want to make this a 0. So we're going to times this by negative 2 or negative 2 R2 plus R3 to R3. So 1, negative 3, 1, 5, 0, 1, negative 1/2, negative 7 over 2, 0, Negative 2 plus 2 is 0. 1 plus negative 1 is 0. 7 plus negative 3 is 4. You can see from the last row, right, 0 equals 4, which is impossible, meaning no solution. So this system of equations have no solutions. Okay. Now the last problem that I want to show you is a system infinite solutions. Systems with infinite solutions. Let's see that. Negative x plus 2y plus 3z is negative 6. X minus y plus 2z is negative 4. 3x minus 6y minus 9z is 18. So we're going to write the augmented matrix, but we want to write the second equation as the first row just to save the work. 1, negative 1, 2, negative 4, negative 1, 2, 3, negative 6, 3, negative 6, negative 9, 18. So we got the 1, we need this to be zeros. So we're going to times this one by 1 and add it to the second row. And then we're going to times this one by negative 3 and add it to the third row. Okay. So the first row isn't changing. We have, that's a 0. Negative 1 plus 2 is 1. 2 plus 3 is 5. Negative 4 plus negative 6 is negative 10. Negative plus 3 is 0. 3 plus negative 6 is negative 3. Negative 6 plus negative 9 is negative 15. 12 plus 18 is 30. Okay, so we already got the 1 here. We need a 0 there, so we're going to do 3 R2 plus R3, give it to R3. Negative 1, 2, negative 4, 0, 1, 5, negative 10, 0, 0, 15 plus negative 15, and then negative 30 plus. So 0 equals 0, that means we have infinite solutions. If that's true, that's infinite. If they're false, then it's... And how do we write the infinite solution? It's not just enough to say infinite. We're going to list the general solution, just like we did in 10.2. So we have x minus y plus 2z equals negative 4, and we have y plus 5z is negative 10, so y is negative 5z minus 10. So we got y in terms of z, and we need to write now x in terms of z. So x minus negative 5z minus 10 plus 2z is negative 4, x plus 5z, if we distribute, plus 10 plus 2z is negative 4, so that's 7z. Negative 4 minus 10 is negative 14, so x is negative 7z minus 14. So the general solution, negative 7z minus 14, y is negative 5z minus 10, and z is c. And that's it for 10.3. We'll talk about 10.4 next.